Okay, I've got 8:30, so let's go ahead and get started. People are still wandering in, but that's okay. Um, okay, so welcome back. Couple of things to note. So you just finished quiz 3 last night. That was due last night. And test 2 will be next week. So make sure you're preparing for that, especially if you feel like test 1 didn't go so well. Make sure you are getting ready for test 2, doing a little bit more review. Make sure you know how all of the CrowdMark stuff works, what to expect. You're signing into your TA meeting, all that good stuff. Many of you had no problems, but a few problems that we had to work out for test 1 that we're hoping not to see again. So, okay. So let's start with our warm-up question. We want to figure out what the GCD of 765 and 476 is. And our tool for calculating GCDs is the Euclidean algorithm. So how does this work? We want to take our bigger one, in this case 765, and we want to use our division algorithm to say that this is something times our smaller one, 476, plus some remainder. So a little bit of quick math. This is, if I double this, I'm going to get at least 800, which is bigger than this, so I only get one copy here. And I just need to do some subtraction. So 5 minus 6 doesn't work. 15 minus 6 is going to give me a 9. I've carried this 1 over, so now I've got 75 minus 47. 75 minus 45 would have given me 30, so this is going to be 28. And I'm at 289 there. Okay, that's my first step. And then my next step is whatever was my last thing that I was dividing by becomes my new left side. And whatever my remainder was is now what I want to divide by. So I've got 476 is something times 289 plus something. Again, if I double 289 is more than 250, so I double 250, I'd get 500. That's too big, so I'm only getting one copy here. And I subtract 16 minus 9 gives me a 7. That 7 has become a 6, so I've got 46 minus 28. 46 minus 26 would have been 20, so I'm at 18, 187. Okay, then we do the same shift over. So this is going to be 289 is something times 187 plus something. Again, this is more than 150. If I double it, I would get 300. That's too big, so I'm only getting one copy. Now my subtraction is a little bit easier. 9 minus 7 is 2. 28 minus 18 is 10. Shift over. Double this, I'd get 200. That's too big. 87 minus 2 is 85. My 100 cancels. Shift over. Oops, spoilers. Only 185 goes into 102. How much is left over? 15 and an additional 17 to get up to 102. And shift over. Now this one's a little bit harder. How many of these can I fit in? So 17, I can double it, I'll get 34. I can even double 34 to get 68. I'm still good. 68, I add another 17. I get 78 plus 7 is 85 exactly. So that's a total of 5 copies of 17. That's 50 plus 35 is 85 with a 0 left over. Okay, so I've got my 0 remainder, which means I get to stop. What is, now that I've done all of this, what is the GCD of 765 and 476? 17. Also got a 5. Another 17. Okay, good. Starting to see some 17s. So I agree. GCD is not 5. We can check that just by looking at the numbers. 5 does divide 765. 5 does not divide 476. Right? It doesn't end in a 5. So we know it can't be 5. It is the last number, not our last multiple, but it's the last number that goes in evenly. When we divide 85 by 17 and get a remainder of 0, that makes 17 our GCD. And that's because what we're saying is the GCD of 765 and 476 is equal to the GCD of 476 and 289, which is equal to the GCD of 289 and 187, which is equal to the GCD of 187 and 102, GCD of 102 and 85, the GCD of 85 and 17, and finally the GCD of 85 and 17 is 17. So that's where we stop and we go all the way back up, and 17 is our GCD there. Yes, that is going to be our next topic of conversation. So this is the GCD. We have done the Euclidean algorithm. That is the Euclidean algorithm. That's how it works. The next thing I want to talk about is something called Bézout's lemma. But this is also the Euclidean algorithm in reverse. So what does Bézout's lemma says? Bézout's lemma says if the GCD of A and B is equal to some number D, then there exists x and y, both integers, with a solution to the equation ax plus by is equal to d. So if I have the GCD, then I'm able to solve an equation like this. This is, by the way, called a diophantine equation. So, quick recap. This is one equation with two unknowns, x and y. So there are infinitely many solutions if we don't care about x and y being integers. If I just let x and y be any real numbers, then I can solve for y in terms of x. I can say y is equal to d minus ax divided by b. I get a nice linear equation. But this is for x and y, both real numbers. If I'm focused on integer solutions, this is where Bézout's lemma comes in. So how does Bézout's lemma work? Why is it the Euclidean algorithm in reverse? Well, I want to show that 17 is a multiple of 765 plus a multiple of 476. And I can do that by reading these equations from bottom to top. I don't need this last one. I start one up. And I rewrite this equation as 17 is equal to 102 minus 85. right? All I've done, I said this says 102 is 85 plus 17. All I've done is move the 85 to the other side. And now I move a step up. And in this next step, I'm going to find a better way of writing 85. So this side's never going to change. This is still 17 equals. And I'm going to leave my 102 for the moment. But now, instead of writing 85, I'm going to say, what's 85 equal to? 85 is equal to 187 minus 102. So instead of 85, I have 187 minus 102. And now, if I simplify, I have a minus 102 becomes a plus 102. I have one copy of 102 and a second copy of 102. So I have 2 times 102 minus 187. Now I go another step up. Keep writing 17. And I'm going to keep my 187, but this line gives me a better way of writing 102. 102 is equal to 289 minus 187. So this is 2 times, because I keep my 2 times, 289 minus 187, and then I still have this minus 187 from before. And again, I can combine some like terms. I have minus 2 times minus 187 minus an additional 187 gives me 2 times 289 minus 3 times 187. Okay, next line up. Still 17 equals. What number am I going to replace in this line? Who's following along? This line gives me a better way of writing what number? 187. Good. Everybody's awake this morning. I like it. So I keep my 2 times 289. That's not changing. And now I have minus 3 times, but instead of 187, I want 476 minus 289. And so this is going to be equal to, I have 2 copies of 289, minus 3 times minus 1 gives me 3 more copies for a total of 5 copies of 289, minus 3 copies of 476. We're getting close. 476, one of the numbers I want. So my very last line, 17 equals. Now I'm replacing this 289. I get 5 times 765 minus 476 minus 3 more copies of 476 gives me 5 times 765 minus 5 minus 3 is minus 8 times 476. So here is my equation that I claimed existed. 17 is equal to a multiple of 765 plus a multiple of 476. In this case, A is 5 and B is minus 8. But they're both integers. Okay, I want to do this again. I want to do it with a smaller example, so it's a little bit easier to track what we were doing. There. Okay, so let's try this again. Let's look at GCD of 60 and 25. Okay, so we start with our forwards Euclidean algorithm. 60 is equal to something times 25 with a remainder. In this case, doubling 25 gives me 50, so that's okay. Tripling 25 gives me 75, that's too big. So I get 2 copies of 50, 2 copies of 25, which gives me 50, with 10 left over. Shift everything over. 25 is equal to something times 10 plus something. Again, I can fit 2 copies of 10 in there, with 5 left over. And now shift over, shift over. I can get 2 copies of 5 with 0 remainder. Okay, so that tells me what my GCD is. GCD is 5. Can happily stop there. But now I want to find a combination of 60 and 25 that adds up to 5. So I'm going to do my Bézout's lemma, my Euclidean algorithm in reverse. Skip the last step. This step tells me how to write 5. 5 is 25 minus 2 times 10. And now I go a step up, and I get a better way of writing 10. This tells me 5 is 25 minus 2 times, I keep my 2 times, 60 minus 2 times 25. And if I simplify this, I get, or distribute this, I get minus 2, another minus 2 gives me 4 copies, plus a 5th copy, 5 times 25 minus 2 times 60. And this one is easy to check. 5 times 25, that's 100 plus 25, so 125. 125 minus 2 times 60, that's 120. 125 minus 120 does indeed give me 5. So my Bézout's lemma works, and I've got an answer to the question, what values of x and y, both integers, satisfy 60x plus 25y is equal to 5. I can say x is equal to minus 2 and y is equal to 5. Shouldn't that be 5 times 25? I'm not sure what you mean. This is 5 times 25. Okay. All good. Okay, so as a consequence of Bézout's lemma, we get the following theorem. In fact, the only time we have integer solutions, so if A, B, and C are all positive integers, then there exists integers x and y such that ax plus by equals c, if and only if the GCD of A and B divides C. So Bézout's lemma says if your C is equal to the GCD, then you can do it. And now this theorem is going to say, in fact, the only cases where this does work is where C is a multiple of GCD of AB, where GCD of AB is a divisor of C. Okay. So let's prove this. So first of all, if D divides A and D divides B, then we have one of our theorem 3.3s. Theorem 3.3, I want to say F offhand, but I'm not sure. But part of theorem 3.3 says that D divides ax plus by for any x and y in the integers. And the GCD certainly divides A and B, since the GCD of A and B divides A, and the GCD of A and B divides B. This means that the GCD of A and B divides ax plus by, but that's equal to C. That's the whole point. So the GCD of A and B does divide C. Okay. So we've proven the forward direction. If there is a solution to this equation, then the GCD divides C. That part is true. Put a little forward direction there. So now we just need to do the reverse direction. Now we need to assume that the GCD of A and B divides C and show that a solution exists. Okay. So now we assume that the GCD of A and B divides, not equal to, divides C, or C is equal to some multiple, let's say K times the GCD of A and B. Well, we know Bézout's lemma tells us that there is a solution A1x plus B1y is equal to D. Right? Bézout's lemma says, sorry, not D, GCD. GCD of A and B. Sorry, x1, hold on. Let's try that one again. Notes don't make any sense here. Okay, Bézout's lemma says that we can find a solution x1 and y1 so that A times x1 plus B times y1 is equal to the GCD of A and B. There we go. That makes sense. And now I just want to multiply everything through by this number k. So A times kx1 plus B times ky1 is equal to k times the GCD of A and B, which we said was C. And since x1 and y1 were integers, k times x1 and k times y1 are also integers. So we set x equal to k times x1, y equal to k times y1, so that ax plus by is equal to c. And now I've done the reverse direction. If GCD of a and b divides c, that's what I assumed, then there are integers x and y that satisfy this. Okay. So I've shown both directions. I showed my forward direction, and now I've showed my reverse direction as well. So there was a question on the quiz, something like, which of these has possible solutions, given that the GCD of these two numbers is blah. We were looking for when the thing you were trying to set equal to was a multiple of the GCD there. Okay. Pause there for questions. How are we feeling? Or do we keep going? Okay, I'm gonna march on then. So let's jump back a bit. We said that GCD of 60 and 25 is equal to 5. And we saw that 60x plus 25y equals 5 has the solution x equals minus 2, y is equal to positive 5. Is this the only solution? Are there any other ways of getting 5 out of here? Okay, we have a no. It's a claim, bold claim. I believe the no a lot more if you can give me an example. Anybody come up with another solution that'll work? Different values for x and y. If I multiply both x and y with the same constant, I'm going to run into trouble. So if I double x and y, I'm also going to double this 5 and get out a 10. So that's not going to quite work. Let's just see. Let's try some values. Let's see if we can figure out something that works. Minus 10, 25. Does that work? Interesting. Yeah, good. Good. So x equals minus 10. Y is equal to 25. This is a relatively nice one. 60 times minus 10 is minus 600. Oh, I don't think it quite works, though. So this is minus 600 plus 25 squared is 625. So this actually comes out to be 25, not 5. So not quite, but close. Minus 1/3 and 1, but minus 1/3 isn't an integer. So we're not allowed to use minus 1/3. 3 and minus 7. There we go. That's the one I was looking for. This is the other one I think pretty easy to find by hand, or doable to find by hand. If x equals positive 3, now I'm at 180. And 180 minus 175 gives me 5. So minus 7 ends up working here. 180 minus 175 gives me 5 left over. So I have at least 2 solutions. And it turns out that there are infinitely many solutions. And what's the trick? What is it that I want to do? I want to add and subtract the same number. To get other solutions, add and subtract same number. So I want to add some number of 60s and then subtract off some number of 25s and have everything cancel. So 25, that's 5 times 5. And 60, that's 12 times 5. I knew that 5 was the GCD. So I knew 5 was the biggest common denominator, the greatest common divisor. And that means that 12 times 25 has to be equal to 5 times 60. Because 12 times 25 is 12 times 5 times 5. And 5 times 60 is 12 times 5 times 5. So these two numbers are the same. So this means if I add 12 25s and subtract 5 60s, I haven't changed my answer at all. So this gives us a way to come up with more solutions. I pick my original solution, x equals minus 2, y equals 5. 5 equal, so 60 times minus 2 plus 25 times 5. Yep, let me finish this and then I will go back and explain it again. But now I'm going to, for every 5 copies of 60 that I add, I'm going to subtract 12 copies of 25. Okay? So again, I'm going to go back in 1 second, but let me just show you why this works. If I distribute I get 5 is equal to 60 times negative 2 plus 300 z plus 25 times 5 is 125 minus 25 times 12, that's 250 with 2 more copies of 25 is 300 minus 300 z. These two cancel out. And I get negative 120 plus 125 gives me 5, which works. So any value of z that I pick makes this equation true. So okay, where did I come up with this? My whole goal is I know that 60 times minus 2 plus 25 times 5 gives me 5. That was my original solution. That's what I found with Bézout's lemma. When I did my GCD in reverse, my Euclidean algorithm in reverse, I got this solution. And now here's the trick that I want to do. I want to factor out the GCD from each of these numbers. So I know the GCD is 5. 25 is what times 5? It's 5 times 5. 60 is what times 5? It's 12 times 5. So what 25 and 60 have in common is the 5. What they don't have in common, what makes them separate, is 60 is a multiple of 12, and 25 has this factor of 5. That's what's differentiating them. And so if I want to figure out how many 60s cancel how many 25s, I need to swap the things that they're missing. So 12 copies of 25 will be 12 times 5 times 5. And 5 copies of 60 will be 12 times 5 times 5. That's how I know this is going to give me the same amount. So now when I'm trying to find my alternate solutions, I'm saying start with negative 2 copies of 60 and add 5 as many times as you want. But every time you add on 5 more 60s, you need to subtract off 12 more 25s, and those will end up canceling out. And so now if I put in any value of z, any integer for z, I get a new answer to my equation 60x plus 25y equals 5. So if I try z equals 1, then this says that 5 is supposed to be 60 times negative 2 plus 5 gives me 3, plus 25 times 5 minus 12 gives me minus 7. That's our other answer that we found. But I can also make z equals 2. Z equals 2 is going to give me a new solution. So 5 times 2 is 10, minus 2 is 8. And then plug in 2 here, 5 minus 24 gives me negative 19. There we go, I've got another answer. I can even do negative z. That is negative 1. This works out as well. Negative 2 minus 5 more gives me 60 times minus 7 plus 25. So 5 minus negative 12 is 5 plus 12 is 17. This even tells me things like 5 is 60 times 498 plus 25 times 1200 minus 5, negative 1195. Right? This was not a solution we were going to guess, but it works, and this equation tells me that it works. Lets me find it. Questions there? If not, let's go ahead and pause for a second. Get a stretch, get some water. So here z does have to be an integer. If we don't pick an integer, then it's still true for any real number. But if you don't plug in an integer, you won't get out an integer. If you try z equals 1/5, then sure, you get negative 1 here, but you get 5 minus 12/5, which is not an integer here. So real number, but not an integer solution. Okay, let's take 2 minutes break. We'll come back 9:11 Winnipeg time. We'll keep going. We will announce test 2 coverage relatively shortly on UM-Learn, just like we did for test 1. I'm going to take a drink of my water. Yeah. Yeah, so it's worth thinking about, right? Right? Like Bézout's lemma. You learned about Bézout's lemma today from me. And I learned about Bézout's lemma from a man named John Mackey in 2010. And John Mackey learned about Bézout's lemma from somebody at some point. He didn't come up with it. And you could trace this all the way back to some guy named Bézout, probably French. Maybe not. I don't know. I don't know the origin of Bézout's lemma. And I guess, yeah, he was playing around with some algebra and came up with the idea first. Or, the way things actually happened back in the 1700s, somebody else came up with the idea and Bézout published it, and then it was named after him. Sometimes, even if you come up with it first, your name doesn't get attached, which is sad but true. Okay. Got 11 minutes past the hour. Let's gather back again. Refocus. So I want to shift topics. Go to a new page. I want to talk about the fundamental theorem of algebra. We're going to abbreviate FTOA. So the fundamental theorem of algebra says every integer n that is bigger than 1 can be written, and this is important, uniquely as a product of prime numbers. Now, when I say uniquely, fundamental theorem of, not algebra, of arithmetic, apologies. Wow. It's a morning after break. Double check, because now did I write it wrong in my notes? Doesn't seem like algebra. It definitely seems like arithmetic. Definitions and theorems. This is why we've got the document. And fundamental theorem of arithmetic. Still an A, just a different A. Ooh, good morning. Arithmetic. Fundamental theorem of algebra. Different theorem. Also good, just not what we're talking about today. Yep, in the doc it says arithmetic because arithmetic is the right one. Good catch. Okay, let me start this again then. Every integer n greater than 1 can be written uniquely as a product of prime numbers. When I say uniquely, I should explain what I mean. I mean the prime numbers are unique, but the order is not unique. You can multiply things in any order you want. So I will say up to the order of the factors. Okay, so talk about some examples. 12, supposed to be able to factor 12 all the way. 12 is going to be 4 times 3, but 4 is going to be 2 times 2. So I have 2 times 2 times 3, or 2 squared times 3. Can look at something like 36. 36 is 3 times 12, which means I've got the same prime factorization of 12 with an extra copy of 3. 2 squared, 3 squared. got 34. 34 is a copy of 2 in it. Afterwards, I just have a 17. So 2 times 17. You can even pick, a bigger number, like 360. So 360, well, I've already done 36. 360 is 10 times 36. So it's all the factors I had for 36 and all the factors for 10. 10 is 2 times 5. So this is going to be 2 times 2 times 2 times 3 times 3 times 5. Or 2 cubed times 3 squared times 5. And so the fundamental theorem of arithmetic is that if I take any integer n bigger than 1, I can break it down uniquely into a product of prime numbers. Now, it's worth noting this is even true for prime numbers. I take a prime number, that's just itself. This is a list of prime numbers being multiplied together. Okay, I don't want to prove the fundamental theorem of arithmetic. I just want to talk a bit about what the proof looks like. So, proof idea. The idea of this proof is that it's going to be similar to our proof that for every integer n bigger than 1, there exists a prime that divides n. So remember how we did this, and then that's going to get us, by induction, okay, we can keep dividing out and getting primes. We're also going to have to use uniqueness somehow, and that's going to come from the division algorithm. So I want to talk about what I did right here. I did not write down a proof of the fundamental theorem of arithmetic. What I wrote down was a roadmap for our proof. It's a suggestion of how you could go off and prove it. And I do suggest you think about it. I suggest you go back and look at our proof of there exists a prime p divides n. Go back and look at how we did uniqueness in the division algorithm. Remember, the division algorithm proof was quite long. It took a lot of time to do it. So think about how you would prove the fundamental theorem of arithmetic. Maybe even try and write down a proof, and then you can read in the Grimaldi textbook their proof there. But I didn't want to do a whole 40-minute proof again like we did for the division algorithm. This is just to give you a few rough ideas of what it entails. But let's talk about some things we can use the fundamental theorem of arithmetic for. So here's a theorem, pretty useful theorem. If p is prime and p divides a times b, then either p divides a or p divides b. So I have a prime number dividing a product. It can't be that part of the prime divides one of the numbers and part of the prime divides another one of the numbers. The idea is that prime numbers can't be broken up further. Prime numbers are these building blocks, they're indivisible, and they build up everything else. So let's prove this. If P divides A, then we're done. By the rule of disjunction or one of those laws of logic, then P divides A or P divides B, right? If we have P divides A, then we get this or, so we are done. So we can work in the case where P does not divide A. If P doesn't divide A, and P is a prime number, what is the GCD of P and A? Yeah, good. Seeing a couple ones in the chat. Then the GCD of P and A is 1. So this is a tricky step, but it's a common step, so it's a good one to see. P, if we write out the list of primes, the list of divisors for P, it's just 1 in P. And if we write out the list of divisors for A, who knows? Could be any number of things, but it doesn't have P on it. That list does not have P on it because P does not divide A. So our only other option is 1. That's the only divisor in common for both P and A. Okay. Well, we've just seen that if the GCD of P and A is 1, Bézout's lemma says that there exist integers x and y such that 1 is equal to ax plus py. And also, since P divides A times B, I know that A times B is equal to P times K for some K. Okay, so I'm using my information. Because GCD of P and A is 1, Bézout's lemma says I can write this. Because P divides A and B, I can write this. And this is all good so far. Maybe this GCD of P and A equals 1 was a little tricky. Here's where the big genius step of this proof comes in. This is the step that I'm just going to write down, and it just looks like, oh, this is the next thing you do. But how the heck did I come up with this? Well, I read somebody else's proof, and somebody else came up with this idea. This is why writing proofs takes practice. This is why writing proofs takes some scratch work. You're seeing the finished product. You're not seeing coming up with this idea. The idea is that I'm going to take this equation right here, and I'm going to multiply it by b. Multiply both sides by b. So b is equal to b times ax plus b times py. All right, fine. I'm allowed to do that. And now b times ax has an a times b in it. And I'm allowed to replace a times b with p times k. So this is equal to p times k times x. plus p times b times y. And the last step of this is I can factor out my p. All right, I did a lot there. This is the step of the proof that's hard to come up with. I took this equation. I know that a times b is equal to p times something. I multiplied this whole equation by b. I found an a times b, so I replaced it with a p times k. And the reason I did all of this was because now both of these terms have a p in it and I can factor them out. So what have I done? Call this number c. I've written b is equal to p times c. So therefore, p divides b. If p divides a, I'm done. If p does not divide a, I've concluded that p divides b. So there's two cases. If p divides a, we're good. If p does not divide a, I've just shown p must divide b. And so in this case, we also have p divides a or p divides b, right? Law of disjunctive something, something. And again, we're done. Or p divides a and p divides b. So we are done in this case too. I like this proof. It's slick. It's clever. Right? Gotta come up with this idea, but once you do, it looks so nice. Okay. We're going to use this in a second, and then we'll get back to using fundamental theorem of arithmetic. But first, I want to do another proof. I want to prove something that you know, but you didn't know you knew how to prove. So theorem, square root of 2 is not rational. This means there do not exist, it is not the case that there exists a and b both integers such that a over b is equal to the square root of 2. You cannot write the square root of 2 as a fraction with integers on both parts. Okay, so this is something you know, right? If you plug square root of 2 into your calculator, 1.414, blah, 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 blah. Goes on forever, doesn't repeat. But how do we know that? How do we know it's not rational? So we're going to do this with a proof by contradiction. Our contradiction starts with assume, for sake of contradiction, or AFSOC, if you prefer. Assume for the sake of contradiction that our theorem was wrong. So assume for the sake of contradiction that square root of 2 is rational. Say square root of 2 is equal to a divided by b. Okay. Then square root of 2 times b is equal to a. Or I can square both sides. 2 times b squared is equal to a squared. Okay. So if we take a look at this equation, what we know for sure that this side is even. Because it has a multiple of 2. So if these things are equal, this side also has to be even. Two must be a multiple of a squared. Since 2 is prime, our last theorem says 2 divides two things being multiplied together. Since 2 is prime, it has to divide a or it has to divide a. But of course, that's the same thing. So since 2 is prime, 2 divides a. Or a is even. Okay. Or in other words, a is equal to 2 times c for some integer c. Okay, so I'm going to use that information in this equation. 2b squared is equal to a squared, but a is an even number, so this is equal to 2 times c squared, or 4c squared. But then I can divide both sides by 2 and get b squared is equal to 2 times c squared. So same rationale as we had before. This side is even. There's a multiple of 2. I can see it. It's right there. So that must mean that this side is also even. 2 divides b squared. Same reasoning. 2 is a prime. 2 divides a. Since 2 is prime, 2 divides b, or b is equal to 2 times d. Oops, not 2 divides d, 2 times d. And now here's where I've run into a problem. I have the square root of 2 is equal to a divided by b, but a is 2 times c, and b is 2 times d, so I could cancel my 2's and get a simpler fraction. But there's a problem here. The problem is, now I could do the same thing, right? I could replace a and b with c over d. I could do this whole same process, and I could get another copy of 2 that I could cancel out. And according to this, I can keep canceling out powers of 2 forever. And that's an issue. If a and b are in lowest terms, they can't share any common factors. So eventually, we reduce to lowest terms, which do not share a common factor. Right, you can only reduce fractions so many times, and then we get a contradiction. You cannot keep reducing but this says you can always keep reducing. This says you can always find another copy of 2. So since we got a contradiction, our assumption that square root of 2 is rational must have been wrong. We can only conclude square root of 2 is not rational. Okay, questions there? Questions about that proof? So you can, quick review of this last part. Sure, so eventually we get to lowest terms, right? We've written square root of 2 as a fraction. You can reduce fractions to the lowest terms. When you reduce fractions to the lowest terms, they have nothing in common. The numerator and denominator don't share any common factors. But this process says you can always find a common factor of 2. You can always say that the numerator and denominator are both even. So eventually we reduce to lowest terms. That means no common factors. But this says you can always find a common factor of 2. That's a contradiction. If you get a contradiction, if you assumed that square root of 2 is rational, and you got a contradiction, that means our statement square root of 2 is rational implies falsehood. So one of our deduction techniques is, from this, we can conclude not square root of 2 is rational. This is one of our laws of logic, or laws of inference, rather. This is our proof by contradiction technique. Yes, so really good observation in the chat. Very, very nice. If I replace 2 with any other prime number, this same proof is going to look exactly the same, just changing out all my 2's for whatever that prime number is. This does not tell us that square root of 6 is irrational. That would need a different proof. Still possible to prove it. It's a little bit more complicated. And obviously this does not always work, because square root of 9 is a rational number. But it does work for any prime number. Okay, I got a couple more minutes. There's one more thing I want to talk about. I want to use the fundamental theorem of arithmetic to help us with GCDs. So if I look at n, capital N because it's a big number, 2,431. I know the fundamental theorem of arithmetic says I can factor that. If I do, it comes out to be 11 times 13 times 17. And here's my question. How many divisors does n have? It's a big number. Seems like it could have a lot of divisors. But it's actually not so many. We know 1 is always going to divide n. And these are all prime numbers that divide n. So we definitely have 11 and 13 and 17. And now it can get a little tricky, because I can also pick 11 times 13. All right, if I take n divided by 11 times 13, I get 17. So that's another option. I can also do 11 times 17. I could do 13 times 17. And there's one more. What's the last number that divides n? Itself, right? All three of them. And 2, 4, 3, 1, or 11 times 13 times 17. So I can list out all the divisors of n by looking at its prime factorization. Right, let's do another one. If I look at capital M, if I make this 26,741, which I've factored for you as 11 squared times 13 times 17. Well, anything that divides n also divides m, because m is a multiple of n. And so how am I changing my list? I have everything from before. But what are my new divisors? The new ones are the ones that have 2 copies of 11. None of these had 2 copies of 11 in them. So anything here that has 2 copies of 11 I want to include. So also 11 squared. Also 11 squared times 13. Also 11 squared times 17. And the last one is m itself. 2, 6, 7, 4, 1. Or 11 squared times 13 times 17. So here I had 8 divisors. Here I had 8, 9, 10, 11, 12 divisors. What's our general rule? If my fundamental theorem of arithmetic says that my prime factorization for capital N is prime 1 to the power e1 times prime 2 to the power e2 all the way up to prime k to the power ek. This is from my fundamental theorem of arithmetic. Then n has 1 plus e1 times 1 plus e2 all the way up to 1 plus ek divisors. Because I can pick 0 or 1 or 2 or 3 all the way up to e1 copies of p1, and I can pick 0 or 1 or 2 or 3 all the way up to e2 copies of p2. For each prime number, I get the number of that prime plus 1 options to choose from. The plus 1 accounts for the 0. So this tells me how many total divisors there are. And this is nice because it can help us calculate GCDs way faster. The Euclidean algorithm is nice, but even faster if you already have a prime factorization. What is the GCD of 2 cubed times 3 times 5 to the 4th times 13 and 2 squared times 5 to the 6th times 7 squared? So this number is 195,000, and this number is 3,062,500. If we wanted to use the Euclidean algorithm on this, it takes 7 steps. And there's a lot of multiplication involved. Like, how many factors of 195,000 really go into 3 million? Right? Little tricky to calculate that. Might take some guessing and checking. But if I look at all the factors of these two numbers, what's the largest number of 2's that both of these numbers share? So 5 to the 4th works. but they both have two. They both have two powers of 2 in them. Right? This has 3 copies. This has 2 copies. So 2 copies show up twice. This one has a 3 and this one doesn't. This one has 4 copies of 5. And this one has 6 copies of 5. So they share 4 copies of 5. This one has some 7s. This one doesn't. Neither of them have any 11s. This one has a 13. This one doesn't. 2 squared times 5 to the 4th, or 2,500, is my GCD. So if you have, the fundamental theorem of arithmetic says that you can factor into prime numbers. If you have that factoring into prime numbers, you can calculate GCDs really quickly. Because you're just asking, what are the prime factors in common? The GCD is going to have a prime factorization as well. It's going to have the smallest number for each prime power that these two share. Okay, I've gone a minute over. Sorry about that. Thanks for your extra time. See everybody on Thursday.